Hello again, everybody. Now we have a second session of three presentations, and the first speaker is going to be Álvaro Serrano. Álvaro is also a graduate from Ingenieros de Caminos as a civil engineer from this school in 2002, and he is the director of a design and consultancy company called MC2. And they have done a lot of work in civil engineering structures and bridges in particular, and also very notable work in building structures. He is also a visiting lecturer or profesor asociado in this university, in another school of this university. So Álvaro, it's all yours.
Thank you very much. Thank you very much. First of all, I would like to say thanks to the organization committee for inviting me to this workshop. Well, we are talking about the design of bridges. We are talking about the aesthetic, the methodology to design a bridge in a proper way. But I would like to call the attention to the erection process of bridges. When we build a bridge, the bridge is not directly in the space that we want to put it on, but it has to be built. Okay, we can see in the image the wonderful viaduct of Millau. That is perhaps one of the highlights in the field of bridges that have been built in the last 10 years. And we always see the image in which the build has been already built. But how to build it? Because the height of the pier is almost 300 meters, and it's not easy for sure to put the deck of the bridge at that height. Okay. Then the erection process, in my opinion, it has to be considered from the very early stages of the design, because if we don't do that, most probably we can reach a good design, but not really good bridge, because the erection process in the design of a bridge is an intrinsic concept to be taken into account. Well, when we build a bridge, we can have a very high pier from a valley, or a very short access in the abutments. We can see this great bridge from the Carlos Fernández Casado office too. And of course, the pass along a reservoir that can be empty or perhaps can be full. Well, then we have to combine both disciplines, not only the design of a bridge, but also the construction method that we have to use to build that bridge. From one point of view, we can see some kind of very conventional or useful solutions to make a bridge, with precast beams or perhaps with a propping system. And in the other way, we can see kinds of solutions in which only the design has been taken into account. Well, when we see this overpass over the highway, beside this, there is no conceptual or structural reason to do that design. We don't know how that overpass has been already built. And when we see, for example, the Alamillo Bridge in Sevilla, we know that in that bridge, first the deck was built, and later the pylon was erected. That has no sense from a structural point of view. Between them, combining both the construction knowledges and the design of bridges, we can see these both bridges. Well, the viaduct of Millau was built by incremental launching, and the second bridge, the San Sebastian Bridge, was built using not temporary, but a temporary arc that was included later in the final structure. Perhaps the first, not the first, but one of the most significant examples that has been built in Spain, in which the erection method has been considered in the design, was the Martin Hill viaduct over the Esla in Zamora. Okay, this was a design that was built, designed before the Spanish Civil War, and it was considered to be built by means of a propping system like the old ancient Roman bridges that was completely destroyed by a flood during the war, because the works was stopped at that age. After the war, the design was conducted by Eduardo Torroja, and he designed a new arch to be able to cross the reservoir in a steel structure that was later used to build by sections the concrete arch. And that steel structure was, to say in that way, the reinforcement or the inner structure of that arc. When the arc already built, it was easier to construct the deck over that. Well, I would like to speak about the erection process in composite bridges. Why composite bridges? Because they are composed of two structural elements. A steel part that is usually considered to take into account the tensions in the deck, and also the concrete that is usually considered to be the element along which the traffic pass. Then the steel has a very important advantage that the steel elements are light and easy to handle, while a precast beam made of concrete can weigh more than 100 tons or even more. A steel deck with the same length and weight can weigh only perhaps 20 or 30 tons. Also, the steel elements can be autonomous to resist the loads that goes over there. From other elements, I am considering the precast slab or even other elements of the bridge. And also the combination between steel and concrete in composite bridges allows to use every material in the better way, with the tension in the steel and the compression in the concrete. Then we are going to pass along three examples: the bridge over the Paredes Strait, in which we are going to see the launching method with abacus; the fourth bridge over the Urmia River, a bridge that has been built quite a long time ago, but I think that is a good sample to build a bridge in an urban context; and also the Comercio bridge here in Madrid, going out the Atocha station. Well, to begin, I would like to say what we call the abacus method. When we have a bridge or a viaduct along a valley, there is usually a main course or a river or a main span to cross over it. And usually there are several spans to approach to the main viaduct. It's not usual to use the same depth of the deck for the whole length of the bridge, because the bending moment laws is usual to be adapted to the depth of the bridge, and then we use a variable depth in the main piers at both sides of the main span. Well, this means that if we want to erect that bridge, for example, with an incremental launching method, we have to make something special in this zone to be able to pass along that variable depth. But, for example, what we can do is to separate the constant depth deck and the variable zone in which we need a higher resistance of that sections, and do something like this, to put at the top of the main pier an abacus. Well, what is the advantages of this abacus? Pues two. The first is that this abacus can be combined with the constant depth section at that zone to make a, for example, double depth section to resist the higher bending moments. And the other one is that if we want to launch this deck along that piers, this element of abacus can reduce the maximum cantilever between the pier before the main one and the main one. Well, the first example of this is for the viaduct over the Paredes Strait. We can see here that the main obstacle in this case is not a river, but is the presence of a way, a road, a conventional road, and we need to span more than 100 meters with adjacent spans of almost 100 meters. Well, if we do a variable depth steel deck, we will have to put that deck along the whole length of the viaduct. But what we can do is to design that steel deck for the approaching spans with a length of 72 meters, and to use that abacus at the top of the main piers to increase the stiffness of that sections, and also to be able to reduce the maximum cantilever between the pier number 2 and the pier number 3. Okay, so we can see here what I am saying about the abacus. The abacus is an element that can be joined to the main pier, and this element can be designed with a composite structure, or perhaps with a concrete structure, or even this element can be a truss or can be a simply steel element. You can see here the cross section at that point, the steel deck with the constant depth and the abacus that is added at the bottom of the section. Well, why this abacus is an advantage to erect this bridge? It's an advantage because if we have to launch the steel deck, we have 72 meters, we have 88 meters, and 104. But if we use this abacus, the length to be launched in cantilever until the abacus is less than the span to be reached. Then we can launch this deck with always a maximum cantilever of 72 meters. That is one of the more conventional spans to be designed. Well, we can see the deck with the maximum span of 72 meters in the pier 2, later reaching the first point of the abacus of the first main point, and later passing along the abacus. Well, we can see here what I am showing in the former drawing. The bridge going out from the abutment, the main pier with a short span, and the second span of 72 meters, that is the maximum cantilever, not only in this stage of the launching, but in the all stages of the launching. And here we have seen the bridge that has already passed along the first abacus and is going along the second abacus. We can see here that abacus at the top of the pier. We can see that in this case, for example, the abacus is formed by two steel girders with a high depth, and the lower flange is made of concrete because it's a section that is going to be always in Huguen bending moments. We can see here the moment in which the deck arrives at the second abacus is passing along the first one, and we can see that in this way we can put the sliding elements to launch the bridge over the abacus. Logically, this is not the height in which the bridge is going to be used in the final stage, but later when we have finished the incremental launching, the deck is below to its final position. Here we can see the final position of the deck, in which the joint between the constant deck and the abacus has been already welded and has been considered as a solitary cross section. We can see also that what we call a strict composite action being implemented here, and very near to the piers with the maximum holding bending moments. The lower flange is made of concrete, substituting the steel. Well, this method of launching can be also designed not with a composite abacus, but with a concrete one, in which is like a only piece, like a piece that is joined to the pier, and also with an sculptoric intention. Then we can see the Santa Lucia Bridge in Uruguay, in which we have a main span of 88 meters and an approaching span of 72 meters, in which the main piers are built with a concrete abacus at the top of them, and that section is considered as a Huguen bending moment with concrete at the bottom of the section. Well, we can see here how the steel deck arrives or reaches the abacus, and the second abacus is waiting for the steel deck to pass along. And an image of the final visual picture of the bridge, in which it's not perhaps possible to difference between what is a pier and what is the deck, because the main span is forming a frame. Well, the second bridge in which I would like to speak about is the bridge over the Urumea River. This is the fourth bridge over this river in San Sebastian, and it's important because all the previous bridges that have been built in that city are very good, everyone in its epoch of bridge design. The main characteristic of this element is that we have approximately 80 meters between both embankments of the river. And there is no pier in the river. Always to build a statically determined bridge is something complicated, because or we put all the steel deck or all the bridge in one movement over the river, or we have to use temporary piers in the river, and this it was not possible because this is a very important element of the San Sebastian city. We can see that it is also a quite wide bridge, and it is formed in cross-section with two steel boxes joined by steel girder curve as an arc, and a concrete slab at the top of the section. Well, we can see here the final stage of the bridge construction. Then how was this bridge built? It was important to say that to get such a span with only a structural bridge is complicated, because we need to use in some cases something to fix the edges of the steel girder. Then what it was designed was to use that fixation at both abutments to put a primer piece or a primer dowel of the steel decks at both sides of the abutments, and later to close the bridge with a key piece, a key dowel, in which the center span or the middle span of the bridge was completed. This dowel was carried until the position to be lifted like a ship. Well, then we can see here the foundation of the abutments with what we have said before, a fixing cell at both abutments to be able to create a fixing for the first dowel. And we can see here that the first dowel of the bridge was erected by cranes from the both embankments, because these are light and short pieces. When we have both first dowels installed, we can begin to put all the elements that will be used to lift the middle part of the deck. We can see here what we have been called. This is a fixing cell with a compression element, that is this abutment, and a tie that is to resist the counterweight, the counterbalance force that try to move to the river the deck. And we can see here the element used to lift the bridge. In this picture you can see that the bridge is already in the position to be lifted. Here we can see that the center part of the deck is being prepared at the embankment very near to the bridge, and put to float in the water by means of cranes. You can see here that this is a curved element and has to be supplemented with the steel plates to be able any kind of sink of this element. And later this is carried by ships until the positions to be lifted, and lift with hydraulic jacks. We can see here the first steps of the lifting and the latest step of the lifting. In this image, the deck of one side is already installed and is being installing the second one until the finalization of the steel structure of both decks. We can see here image in which one element has been already constructed, and the rest of the erection process is more conventional, because it's simply to put the structure between both decks and both girders and the concrete over that steel structure. We can see here the concreting of the deck into phases, and the bridge already finished. Well, and finally I would like to speak about a bridge that has been built recently here in Madrid at the south part of the Atocha railway station. And the main problem in this zone is that it's a urban zone very consolidated, and there is only very few zones in which we can support or we can put piers for the bridge. Here there is the commercial street that pass below all the railway field, the railway for regional trains, line C5, and the high speed tracks. Then the new alignment of the bridge has to be here, passing over the commercial street and also over the line C5. What that means that we can put one abutment here, another abutment over there, and the only zone in which we can put piers are between the commercial street and the railway line C5. What does mean? That means that the spans between all that points are very different and are also very different between the left side and the right side of the bridge. Well, what we have designed for this point is a bridge, a truss bridge with two trusses that are at both edges of the track, and two abutments, two elements very light, and a sculptoric pile. As I said at the beginning of my presentation, we can see here the bridge already built, but it's quite complicated to put it in his final position along the street, the railway line, and with all the constraints that represent to work in a city. Then we can see better the three-dimensional, because this is a quite wide and very short bridge. These are no more than 100 meters, but we can see here the commercial street, the regional railway line, and we're going to pass over both elements. Then we are going to design one abutment here, another one here, a main pier that is in the street like a milestone of the bridge, and another more conventional piers. From the point of view of the cross section, we have the two trusses that at the short spans this converts in a box girder, and the steel transversal girders to be completed with a concrete slab. Well, how was the erection method design? Well, first of all, we have to build the infrastructure, the foundations of the bridge. That is a quite simple stage, because there is no much constraints in this step. The second one is to build the steel structure in one abutment, because we are going to launch all the structure over the street and the railway line. We can see here that we are going to launch these both steel structures until his final position. We have to say that this last span was built later by means of a crane, because the launching was only from this point until this another point. It's important to say that to launch a steel deck, or in general any structure, it's important to have a straight or constant curve alignment, and this is not the case. You can see that here we comes from the Atocha station with a straight line. We have here a curve, a circular curve, and a transition curve between both elements. That is quite difficult then to launch this element, because we have not a line to make that incremental launching. Well, that was important because there was a lot of temporal operations to do to be able to reach this pier with a straight or curve line. Then we can see here the steel structure of the bridge already built in the first abutment. This is being completed, the whole structural steel, and also the formwork, the steel formwork that will be used later to concrete the slab. Here we can see the elements that will be used, a temporary propping to build the structure. We can see here elements to slide along these rails supporting the whole steel structure. We can see that there are hydraulic jacks at the top of that elements that will support the weight of the steel structure, and you can see here the direction or the alignments that are prepared to be able to reach those temporary bearings when the bridge is launched. Well, we can see here the bridge when have been already arrived the first pier and is passing along it, and another picture of the bridge when it has already finished the launch of the second span, and the maximum height of the truss is also reading the main pier. Finally, when the steel structure has been already launched, is completed with the last span of the bridge, and the concrete layer is put on site by conventional methods. This is the final image of the viaduct that we can see here in Madrid near Atocha. Then to finalize, I would like to remember, to recall a concept that Julio Martínez Calzón, perhaps the main innovator in composite structures in Spain, has been said in his book Puentes, Estructuras and Actitudes. Then the erection process is then a field very open in which great creativity and experience is required to be able to take the advantage in a good manner in every work, not only the usual resources, but also the innovative ones in an integrated and optimum form. Well, thank you very much, and I hope that the erection method in composite bridge will be used and considered in the design of all the bridges that all these promising future engineers will be designed. Okay, thank you.